Good morning, students. In today's session, we are going to discuss the open circuit characteristics of a DC shunt generator. They are also called as magnetization characteristics. Okay. Now, why? What is the need for obtaining magnetization characteristics of a DC shunt generator? What is the information that we are going to get from the magnetization characteristics? So from the magnetization characteristics, we can compute the value of critical resistance, critical speed, and maximum built-up voltage. Critical resistance, critical speed, maximum built-up voltage. Okay. So to obtain these values, we are going to plot the magnetization characteristics. Okay. So critical resistance is the maximum resistance that we can maintain in the field circuit. So if you make the field resistance value more than the critical resistance value, then the generator will fail to excite under no load conditions. It cannot start to build up the voltage under no load conditions. So we need to keep the field resistance of the shunt generator to be lower than the value of critical resistance. Next, coming to the critical speed, it is the speed below which the generator will fail to excite. If you go on decrease the speed of the shunt generator, at certain point, the existing field resistance of the shunt generator will become equal to the critical field resistance. If you further decrease the speed, it cannot able to generate the voltage. So the speed at which the existing field resistance becomes equal to the critical resistance is called as critical speed. And next one is maximum build-up voltage. So what is the maximum voltage that the generator can generate under no load conditions? That value we can obtain from the open circuit characteristics. Okay. So let's see the nameplate details. First, DC shunt motor. We are going to use shunt motor as a prime mover to the shunt generator. For shunt motor, the power rating, HP rating is 5 and voltage rating is 220 volts and current rating, line current rating is 19 amps and field current is 1 amp and speed is 1500 rpm. Now coming to the nameplate details of DC shunt generator that we are having in our lab to do the experiment. Its kilowatt rating is 3 and voltage rating is 220 volts. Next, load current rating is 13.6 amps and field current rating IF is 1 amp and rated speed N equal to 1500 rpm. These are the nameplate details of the shunt motor and shunt generator that we are having in our lab. Now, what is the operators required for conducting the test? One ammeter and voltmeter and rheostats and tachometer are required. Now, what are the ranges that we need to use? For fixing the ranges, go to the circuit diagram. So here, we have to fix the ratings of the meters and other equipment using the nameplate details, and then you can write these values in the operators table. Now, coming to the first, this is shunt motor. This is a motor diagram, and this is a generator diagram. Let's start with motor. The motor, we are providing a DC supply. The rated DC supply voltage in our lab is 220 volts, and the fuse rating as a rating of the shunt motor is 19 amps. You can use 20 amps fuse. Now, coming to the field circuit, we are having one rheostat. and the rated field current is 1 amp as for the nebula details. Therefore, the field rheostat should able to withstand up to 1 amp of the field current. So in our lab, we are having a 300 ohms rheostat, which is variable from 0 to 300 with 1.7 amps 0 to 300 ohms with a variable resistance with 1.7 amps current capacity. 1.7 amps current capacity. So with this, the motor circuit will be completed. Now we'll move to the generator part. Here, the rated voltage that we are going to give as input to the field circuit is 220 volts, and we are using a potential divider in order to apply a variable voltage to the field circuit. So as the rated field current of the shunt generator is 1 amp, here also the rheostat, that is potential divider that we are going to use, is able to withstand up to 1 amp. So I am using same 0 to 300 volts, 300 ohms, 1 amp potential divider. Now coming to the ammeter, as the maximum current is 1 amp, you can use 0 to 1 amp. So here the meter should be of MC type, as the current that going to flow through the meter is DC. So entering terminal plus, leaving terminal minus. And one voltmeter is connected, and as the voltage increased, so complete 220 volts we can apply. Therefore, we are going to use the voltmeter with a range of 0 to 300 volts MC. Now the fuse depends upon the maximum current that going to flow in the circuit. The maximum current is 1 amp, so I am using a 2 amps fuse. So 1 amp is not available, so we are using 2 amps fuse. If 1 amp is available, then you can use 1 amp fuse. Now there is one more voltmeter is pending here. The voltmeter is connected to, positive terminal is connected to A terminal of the generator armature, and negative terminal is connected to AA terminal of the shunt generator armature. Now, try to set the meter range for this voltmeter. So in the experiment, we are going to take the readings up to 120% of the rated voltage. Rated voltage is 220 volts, and it's 120%. We will get 264. So this voltmeter should read the readings up to 264 volts. So as a result, I am using 0 to 300 volts MC type voltmeter here. So this is how we are going to fix the meter ranges for the experiment. Now let's write these meter ranges here. Ammeter, we are going to use a 0 to 1 amp ammeter of one quantity of MC type, and voltmeters 0 to 300 volts range. We are going to use 2 voltmeters. One is in field circuit, another one is in armature circuit of shunt generator. This is also of MC type, and we are using 2 rheostats. One as a potential divider, another one is as a field rheostat. Potential divider is used in field circuit of generator, and field rheostat is used in motor circuit field. Here, the rheostats are going to range from 0 to 300 ohms, 1.7 amps. So they require 2 in quantity, and 1 tachometer, digital tachometer we are going to use. Now, coming to the experimental setup. So we have to make connections as per the circuit diagram. That practical, how we are going to take the readings practically, that we are going to see in practical setup video. And here just I am going to explain how we are going to take the readings. First, we are going to bring the shunt motor to the rated speed by using this field rheostat. And once the shunt motor is going to operate under rated speed conditions, the generator will also operate at rated speed conditions. When the generator is operating at rated speed condition, we have to switch on the DPST2. This is DPST1, this is DPST2. So first DPST1 is closed and we are given supply to only shunt motor. Now we are giving supply to field circuit of the shunt generator. Now by gradually varying the potential divider, we have to take the excitation values and induced EMFs and field voltages for different conditions. So by varying the field current in different steps, for each step we have to note down the field current value, induced EMF and field voltage, and those values should be tabulated. So to understand the calculations, I am taking readings from the old records. So here VF is 0, IF is 0, E0 is 14, and for a field current of 0.1, VF is 20, IF is 50. For 0.2 field current, VF 40, 90. For 0.3 field current, it is 60, 124 is E0. For 0.4 amps, VF is 80, EF E0 is 156, and for 0.5 it is VF 100, whereas E0 is 188, 0.6, 120, 212, 0.87, 140, 232, 0.8, 160, 256, 0.9, 180, 264. So we got the 120% of excitation rated voltage as the induced EMF. So we are going to stop the freezer here. Now from this point, do the calculations. So here RF equal to VF by IF. So VF by IF gives the field resistance, field voltage by field current. So like this, we need to complete the calculations. It is 200. It is also 200. 200. So field resistance we are getting as 200 ohms. Now, if we do the now from these readings, we need to plot the open circuit characteristics and field resistance line, the IF and E0. If we plot between IF and E0, we will get the open circuit characteristics. So if we take field current on x-axis and E0 on y-axis, if we plot the graph between these two, then we are going to get for zero field current we are having 14 volts as the induced EMF. So it won't start from the origin, it starts somewhat above the origin. So we are going to get the open circuit characteristics somewhat like this. Now, afterwards, we need to plot the field resistance line. For that, we need to take IF versus VF. IF on x-axis and VF on y-axis. Plot the curve. It will be a straight line having a slope of 200 ohms. RF has a slope. So the curve will be a straight line. Will be a straight line passing through the origin. When IF equal to 0, VF will be 0. So we are going to get a straight line like this. If both are not intersecting, that means if the OCC is not intersecting field resistance line, just extend with a free hand such that both will intersect. But you should not rise to a large value. So as after saturation, we require large amount of increase in field current in order to get a small increment in the voltage. So it should be of downward trend. Now, from this open circuit characteristics, this is OCC and this is field resistance line. Now, from these two, you can get the value of critical resistance, critical speed, maximum build-up voltage. Now, let's see one by one. First, in order to get the maximum build-up voltage, what we have to do is take the intersection point. So the intersection point of OCC and field resistance line gives the maximum build-up voltage. Corresponding to the intersection point, whatever the voltage is there, take that voltage as OM. O is the origin and M is the point corresponding to the intersection point of OCC and field resistance line. So the value of OM gives the maximum build-up voltage. Next, we need to obtain this OM gives the maximum build-up voltage. From the graph, you need to write the maximum build-up voltage value. Whatever the value that we are getting from the graph, that we have to represent here. Suppose for getting it 280 or 290 volts, so that we have to write here. Next, for obtaining the critical resistance and critical speed, we need to draw a tangent to the initial portion of the OCC. So whatever the linear portion is there, to that linear portion, we have to draw a tangent from origin. So this tangent will be the OCC if saturation does not take place in the machine. If in case if the saturation is not there, then this tangent will become an OCC. So this line is called as air gap line. Air gap line. Now, if we find the slope of this tangent, then we will get the maximum build-up voltage. So to find the slope, let's take a point here. So I've taken this point as intersection with the field resistance line. I'm taking as B. This point with OCC intersection is C, and on x-axis I'm taking it as D. And corresponding to C, the y-axis we're taking as A. Now, from this, we can get the critical speed as critical resistance critical resistance RF equal to field resistance correspond to the tangent. So voltage is CD divided by field current OD. CD by OD gives the critical field resistance value. Similarly, the critical resistance NC equal to BD divided by CD into N. That gives the critical speed. Now, if I take the point at which the OCC starts on y-axis, if I take this point as P, then the OP gives the value of induced EMF due to residual magnetism. It's called as OP. Okay. Now, for example, if I take the field current as 0.2 amps or 0.1 amp. So 0.1 amp calculate చేశాను అంటే at 0.1 50 is the OCC, that is OCC induced EMF. So 50 divided by 0.1 will be equal to 500 ohms. So corresponding to 0.1 amp, the E0 is 50. So corresponding to 0.1, E0 is 50. So this is A 50. So 50 by 0.1 gives the 500 ohms. Now, suppose if it has intersected at suppose around 20 volts, suppose take this value as 20 volts, then 20 by 50 into speed at which the readings are taken. We are taken at rated speed 1500. 0, 0, 30. So 600 RPM will be the critical speed. These are the sample calculations, not the exact values that we are getting from graph. So practically, if you draw the graph, the readings may be differ. Just I am giving how to calculate it. So I am giving you an idea how to calculate only. So it's not the actual value. Now coming to the maximum build-up voltage. So up to here it is 264. So it has increased somewhat. So I am taking it as around 290. This M point is at 290 volts. So OM will be 290 volts. Now OP. OP is the point at which the OCC starts when field current is 0. When field current is 0, the E0 is 14. So OP will be equal to 14 volts. So like this, we need to calculate the critical field resistance, critical speed, maximum build-up voltage, and voltage induced due to residual magnetism. Okay. So this is magnetization characteristics of shunt generator.